What we'll do now is take a look at some different cases involving the use of normal CDF to find an area or a probability. So let's just jump into these cases, and this can be a reference here at the top as we move along. So let's take a look at this first case, finding area between two z-scores. So this would be equivalent to asking, what is a probability of selecting a z-score between two values? So indicated by a lower bound and an upper bound. All right, so let me first start with this one. And we do a lot of sketching of bell curves this semester. So it's always good to get a feeling for what these graphs look like. So on my graph, I'm first going to just put the line down the middle here. The mean is 0 for z-scores. So this is our standard normal distribution. And we want to look at the probability of a z between. So negative 2.25, you can just sort of approximate there. So a negative z-score will be to the left of 0. And then my upper bound is 1.50. So that will be to the right of 0 because it's a positive z-score. And this is the area that would correspond to that probability question. So we'll either word it as an area between them, or what is the probability of selecting a z-score and it being between those two values. All right, so I'm going to indicate my LB here. So lower bound to upper bound. So lower bound's always on the left, upper bound is always on the right. And then when we use our calculator, the function that will find that probability is called normal CDF. We indicate the lower limit, or the lower bound, the upper bound. And then in general, we have to indicate mu and sigma. So in this case, again, with z-scores, if we're dealing with standard normal, the mean is 0 for standard normal, and the standard deviation is equal to 1. Now, it turns out that if we don't type in any value for mu and sigma, then the calculator assumes that's what we wanted. So we call that the default on the calculator. So in other words, if I don't type in any mu sigma, the calculator just assumes this is what I wanted. So with z-scores, we can just type lower bound, upper bound. If we were doing like a churro example, then we'd have to put in the mean for the churros, like the 300 calories. All right, but for z-scores, it makes it a little easier. So just lower bound, upper bound, and then we're good to go. So we go to our calculator, you go back to your distributions, normal CDF, negative 2.25, comma 1.5. You can put the 0 if you'd like. And I'm going to stick with 4 decimal places when we're doing our probabilities here. So that is 0.9209, and then 6 is the 5th decimal. So that 6 makes the 9 round up to 10. So that will be 0.9210. So 0.9120. And we'll tend to stay in decimal here, but I'm just going to put this as a percentage as well. So what I've just shaded on that picture is 91.20% of that bell. So not 100%. So there's still some area over here and over here, but I've shaded a significant portion of that bell, 91.20% of it. All right. So let's try another one. Find the area between z equals negative 2.50 and z equals negative 0.75. So always good to get a feel for what these graphs look like and where your z-scores are. So negative 2.50 is getting pretty far into that left tail. So negative z-scores, again, are left of center because 0 is in the center as a z-score. And then negative 0.75, just kind of approximate there. So that's negative 0.75. So in this case, if we're looking for the area between those two values, so we'll have our lower bound, upper bound. So lower bound is on the left, upper bound is on the right. I'd also like to write this question as a probability question. So we could say find that area, or we could say what is the probability that a z-score is between negative 2.50 and negative 0.75. So it's important to understand that this is the mathematical way to say z is between two numbers. So you have the lower bound, the less than sign, and then the z. So z is between those two values, lower bound, upper bound. And then we go to our calculator. So back to your normal CDF. All right, so negative 2.5 and negative 0.75. And I'll round to 4 places, 0.2204, 0.2204. And I'll write this one as a percent as well. That would be 22.04% of that graph that I've shaded. All right, so before we continue, just one thing to point out at the top in terms of this note. It says, in general, for a probability from a continuous distribution like our bell curves, it doesn't matter if strict inequality or its non-strict counterpart is used. So let me just make a note about that. So the less than sign here is a strict inequality. So what it means by non-strict, if I change this question and instead of saying less than, if that said less than or equal to, and I'll do it with this one too, if that instead of less than was less than or equal to. When we're dealing with continuous distributions, the method is the same regardless of whether or not those were less thans or less than or equal to. So it's very different from discrete, where we spend a lot of time on the differences between a less than versus a less than or equal to. All right, and I just noticed I didn't write down my calculator entry, which I usually do. I'll make sure to do that on the next one. All right, one more of these. So these will be the easy ones. Lower bound, upper bound, when they're numbers like this, we're really just practicing with the graph to get a feel for these graphs because we need them this semester. So let's find the area under the standard normal curve. So standard normal curve are our z-scores and between, all right, negative 1.96. So negative 1.96 is getting close to negative 2. So we're not quite there, but just kind of approximating that. So negative 1.96 and z is positive 1.96. So getting close to positive 2. All right, and we'll often be shading areas. So we're interested in finding that shaded area. It's looking like a big portion of that bell is shaded. I'm going to throw my z on the side here. There's my z-scores. There's our 0 in the middle. So if we want to find that area, that would be also saying what is the probability that a z-score is between negative 1.96 and 1.96. So again, lower bound, upper bound. Lower bound on the left, upper bound on the right, always. And then we can go to our normal CDF, enter our lower bound and our upper bound. And if we don't put in mu and sigma, Standard normal is the default. The calculator will assume that you wanted mu is 0, sigma is 1. All right, type this guy in, and in this case, if we round it to 4 decimal places, it's looking like 0.9500. Now, I'm going to write that as a percent as well. So I'm actually going to leave off the 0.00 and just say 95%, just to remind you that in a previous chapter, we actually dealt with bell curves and looked at the middle 95% of the data. So this was the empirical rule we learned back in a prior chapter. So in a prior chapter, when we said 95% of the data, we actually said that 95% of the data was within 2 standard deviations of the mean. So remember, the center here is the mean. So 95% of the data is within, well, these numbers aren't exactly 2, but with our calculator now, we're just a little bit more accurate than we were before. So in a prior chapter, I would have just called this -2 and 2. But about 95% of the data, that's still within 2 standard deviations of the mean. All right, so that would leave, that's 95% of z-scores. So in these tails, so we're going to call these guys tails. So I'll call that one the left tail and the right tail. There aren't a lot of z-scores left. So if the whole bell is 100%, I'm just going to write 100% would be that whole bell. If I took away the 95% that's shaded, that would leave me with 5% of z-scores. So 95% are in the middle, 5% are left. So if we divide that by 2, it told us how many z-scores, what proportion of z-scores are on either side. So we did this in a previous chapter, divided that by 2, 2.5%. So 2.5% of z-scores would be above positive 1.96. And on the other end, 2.5% of z-scores would be below negative 1.96. All right, so what we'll learn to do next, though, is what if instead of doing all of these parts, the tail in the middle, how could we just find the right tail? So in other words, what if I just wanted to know the probability of a z-score being bigger than 1.96, and I'd like to find that answer using normal CDF. So we'll take care of that case next.